In this video, I want to look at right-hand Riemann sums written in proper summation notation with the capital sigma. To get started, I want to recall the definition of the definite integral. The definition of the definite integral, the integral from a to b of f of x dx, is given by this ugly-looking limit. The limit as n gets big and delta x goes to 0 of the summation as k goes from 1 to n of f of ck times delta x. It's important to remember that what we're really doing, however, is that f of ck times delta x is really nothing more than the area of rectangle K, the rectangle that we put over the kth subinterval when we are doing a rectangular estimation of our area. In other words, if I draw the picture very, very quickly, if I have y is equal to f of x that looks like this, and that's a, and this is b. I chop this thing up, and over the kth subinterval, so I have xk minus 1 here and xk here, I stick a rectangle, and this particular rectangle has this particular area. In the things that we're going to be doing, the delta x is always just going to be b minus a divided by the number of rectangles. And it turns out that the kth subinterval will always run from a plus k minus 1 times delta x to a plus k times delta x. In other words, this endpoint of the kth subinterval is a plus k minus 1 times our jump, which is delta x, and this one is a plus k times delta x. Now, if we want to have a right rectangle estimate, so a right rectangle estimate, and let me clean up my handwriting because that's not very readable. So if I want a right rectangle estimate, what I want to do is I want to pick CK to be the right endpoint of the kth subinterval. So CK is going to be nothing more than a plus k times delta x. And all I'm going to do is I'm going to substitute this in for CK inside this particular definition. And so what I get is the following. Our right rectangle estimate formula will always be the sum as k goes from 1 to n of f of ck, but f of ck now is f of a plus k times delta x times a delta x, where the delta x is nothing more than b minus a over n. Now let's look at a particular example of how this might work. So this is a formula that you should take the time to write down in your notes. And now I want to kind of look at an example for using this. So as an example, let's let f of x be x squared plus x plus 1. And I want to find right-hand estimates for the integral between 1 and 3 of f of x dx. And let's say I would like to have n equal to 5, 20, and 50 rectangles. So I want 5 right rectangles, 20 right rectangles, and 50 right rectangles. Now, if I was just wanting 5 right rectangles, all I would do is I would draw a picture. But because I'm having multiple things, I want to do this with the sigma notation. So my right rectangle estimate is always going to be the sum, as k goes from 1 to n, of f of a plus k times delta x and my handwriting is letting me down again, times delta x, where the delta x is supposed to be b minus a over n. But now what I want to notice is that I actually have values for a and b. The lower endpoint is always going to be a. The upper endpoint is always going to be b. So delta x here is going to be 3 minus 1 over n. That'll be 2 over n. So I'm going to put in 2 over n there, and I can put it in a 2 over n here, and I can put a 1 in here. So my right-hand estimate is now going to look like the sum as k goes from 1 to n of f of 1 plus k times delta x, which is nothing more than 2 over n. And then once I have f evaluated at that, I need to multiply that by 2 over n. Now, as far as this summation is concerned, this 2 over n is a constant. There is no k in this part. That's the only k. So it's going to help me to pull that 2 over n outside the summation sign. So my right-hand estimate can be written as 2 over n times the sum, as k goes from 1 to n, of f of 1 plus 2, well, we can clean this up to read 2k over n. And now I have to remember that f of x, let's go back up and see what it was. F of x is this function right here. So I want to put that in. F of x is x squared plus x plus 1. And as a consequence, what I want to do is I want to evaluate this function at this particular number. So the next step in my work is that my right-hand estimate is going to be 2 over n times the sum as k goes from 1 to n of, well, let's see, I've got this junk and I need to square it. So I've got junk squared, plus I have the junk, plus I have a 1. This stuff inside these square brackets is f evaluated at 1 plus 2k over n. Now, I could leave the answer here if I wanted to, but I do want to kind of clean this up and make it look just a little bit better, particularly keeping in mind that eventually we're going to want to do the full-fledged definition. So I want to just take the time to do a little bit more algebra to clean stuff up. My right-hand estimate, or my right sum estimate, is going to be given by 2 times the sum as k goes from 1 to n of, well, let's see, when I square this mess here, I am going to get 1 plus 2 times 2k over n plus 2k over n squared. Then I have this mess. So I have 1 plus 2k over n, plus I finally have that one there, and now I have the ending bracket for that. And I can clean this up just a little bit more. So my right sum estimate is going to look like 2 over n times the sum as k goes from 1 to n of, well, I want to start with, let's start with the constants. We have 1, 2, 3 of them, so I have 3 plus, let's see, this part here is 4k over n, and then I have 2k over n. So let's see, 4k over n plus 2k over n is going to be 6k over n. And then finally I have this thing here, and when I do that squaring, I am going to get 4k squared over n squared. And this would be a perfectly good right-hand sum for n rectangles. Now it's just a matter of going back and plugging in the three values for n that we had at the beginning of the problem. So let me make sure that I can still see that particular formula. If n is equal to 5, my right sum estimate is going to be 2 over 5 times the sum as k goes from 1 to 5 of 3 plus 6/5 k plus 4/25 k squared. If n is equal to 20, my right sum estimate is going to look like 2 over 20 times the sum as k goes from 1 to 20 of 3 plus 6 over 20 times k plus, 4 over 20 squared times k squared. I could clean this up a little bit if I wanted to. This would be 1/10 times the sum as k goes from 1 to 20 of 3 plus, 6/20 is 3/10 times k. And 4 over 20 squared is 4 over 400, so that will actually be 1 over 100 k squareds. And then finally, my last one, when n is equal to 50, my right-hand sum estimate would look like 2 over 50 times the sum as k goes from 1 to 50 of 3 plus 6 over 50 times k plus 4 over 50 squared times k squared. And at this point, I don't think I really want to deal with the arithmetic, but you could deal with the arithmetic if you wanted to. That's how you're going to be doing problems that ask you to find the summations for right-hand Riemann sums.